Swayamprabha. Digital India. Educated India.
In the previous lecture, we were discussing about the fundamentals of fully developed flow and developing flow in channels, and let us recapitulate what we studied a little bit before proceeding further. So, we considered fully developed flow in a parallel plate channel, and considering that, we started with the continuity equation and the momentum equations to describe the velocity profile, the fully developed velocity profile, which is parabolic in nature. Then we calculated the dimensionless wall shear stress and dimensionless pressure drop, and because the wall shear stress and pressure drop are related, their dimensionless forms are also related. The dimensionless wall shear stress is the Fanning's friction factor Cf, and the dimensionless pressure drop is the Darcy's friction factor F, and we derived that F is equal to 4 Cf. This was what we discussed in the previous lecture, and we will try to extend the discussions of the previous lecture for flow through circular channels, right. In microfluidics, rectangular channels are more common than circular channels, but circular channels are also important in the context of microneedles, I mean which may have circular section. So, it is important to understand the fundamental mathematical paradigm by which we describe the circular flow through circular tubes, the fully developed flow through circular tubes, which is given by the Hagen-Poiseuille law. So, to understand that, let us appeal to this slide which is there. So, in this slide you can see that we have drawn a cylindrical tube. I mean it is better not to call it a pipe because we are considering small dimension. So, we may call it a tube, although like geometry wise there is no great difference, tube of radius r, and we have Vr, V theta and Vz as the 3 components of the velocity. So, here we are using the cylindrical polar coordinate system. The flow is steady, so that del Vz del t equal to 0. The flow is fully developed, so del Vz del z is equal to 0. It is just like del u del x equal to 0 for a rectangular channel. Here the axial direction is the z direction, so the del Vz del z equal to 0, and because of axial symmetry there is no variation with respect to theta. So, if you consider all these, then you will see that if you write the momentum balance, the z momentum equation, then the left hand side becomes 0, just like the left hand side in the x momentum equation becomes 0 for flow through a rectangular channel. Similar thing, the left hand side, which is the acceleration term, becomes 0. Then right hand side there is a balance between the pressure gradient term and the viscous term. Now, the r momentum equation, so far we have discussed about the z momentum equation. In the r momentum equation you have basically all the terms, because Vr is equal to 0, all terms are 0, that means del p del r, which is the only term remaining, that term is also 0. So, because del p del r is 0, that means p is a function of z only, p is not a function of r. So, that boils down to this equation. I am just going through it I mean in a very straightforward manner, because the same thing just in a different coordinate system we have discussed in details. So, I just do not want to spend unnecessary time in describing the same physics for another case where only change is the description of the coordinate system, but physically it is the same. So, you can see that the Z momentum equation, the pressure is a function of Z only and Vz is a function of R only. The only difference between the rectangular channel or the parallel plate channel and the circular pipe is the fact that the viscous term you express, instead of d2 Vz dr2 it is 1 by r ddr r dvz dr. That is just a representation in the cylindrical coordinate system. So, this is because Vz is a function of r, this is a function of r only, P is a function of z, so this is a function of z only. So, function of r is equal to a function of z, that may be possible only if each is a constant. So, we take it up from here and go to the board to address this problem. So, 1 by r ddr of r dvz dr is equal to 1 by mu dp dz. Next, what we do? So, then each is equal to say C. So, we can write d of r dvz dr is equal to C r dr. We can now integrate it. So, if we integrate it now, r dvz dr is equal to C r square by 2 plus C1. So, you can see that dvz dr is equal to C r by 2 plus C1 by r. Now, if you consider the channel or the tube, the center line is r equal to 0. So, at r equal to 0 you must have dvz dr finite, right, but this 1 by r dependence is killing that finiteness until and unless C1 is equal to 0. So, dvz dr must be finite at r tends to 0, which implies C1 equal to 0. So, dvz dr, so Vz is equal to C r square by 4 plus C2. So, we will apply the other boundary condition, that at small r equal to capital R, what is Vz? Vz must be equal to 0. So, that means C2 is equal to minus C r square by 4. So, that means you have Vz is equal to C by 4 into small r square minus capital R square. All right. So, we can now express Vz in terms of V average. So, what is V average? Integral Vz into 2 pi r dr 0 to r divided by pi r square, right, integral V z dA by the area. So, C by 4 into 2 pi into r cube minus r square r dr zero to r by pi r square. So, this becomes C pi by 2 by pi r square into r 4 by 4 minus r 4 by 2. So, this is minus C r square by 8, all right. So, that means you can substitute that expression for V average in the expression for V z, and once you substitute that you get V z by V average is equal to 2 into 1 minus small r square by capital R square. So, this is the velocity profile. Again the parabolic velocity profile is evident from this analysis. Next, what we will do, we will find out either the dimensionless wall shear stress or the dimensionless pressure drop. Let us find out the dimensionless pressure drop. So, you can write V average is equal to minus C r square by 8. And C is equal to what? 1 by mu dP dz, that is 1 by mu delta P by L. Okay. Now, so you can write in place of delta P, we are basically working out the same steps that we worked out in the previous class, just the coordinate description is a little bit different, the geometry is a little bit different. So, this is minus Hf rho g, where Hf is the head loss due to friction. So, V average is equal to Hf rho g by mu L into r square by 8. Okay. So, HF is equal to 8 mu VL by rho g r square, and you can write it in terms of the flow rate by writing V average is equal to Q by pi r square. So, 8 mu Q L by rho g pi r to the power 4. Many times in engineering convention we express the result in terms of the diameter of the pipe rather than the radius. So, if you substitute r equal to d by 2, then we get HF is equal to 128 mu q L by rho g pi d to the power 4. You can find out the friction factor F from here, the Darcy's friction factor, just in the same manner as we in which we calculated in the previous class for the rectangular channel, and you will get F equal to 64 by Reynolds number. So, what we have done, we have summarized the description for fully developed flow, for for parallel plate channel and for circular geometry. So, let us summarize the important findings as we get back to the slides. So, so far we have discussed about the fully developed flow and fully developed laminar flow. So, this diagram I have purposefully put in this context. I mean, you can recall that this is nothing but the Moody's diagram, what you see here, and we will try to understand that which regime is important for us in microfluidic applications. In microfluidic applications, we are, so in the x axis there is Reynolds number, in the y axis on the left side there is friction factor either F or CF, whatever you want to plot, they are related, and the right hand side it is either the roughness by the diameter or the diameter by roughness. In this particular case it is diameter by roughness that is plotted. So, either of the diameter by roughness or the roughness by diameter. Then basically we are operating in microfluidics in the low Reynolds number regime, and in the low Reynolds number regime you have laminar flow. So, this curve CF, so this figure is for a circular geometry. So, CF F was 64 by RE, so CF is F by 4, so 16 by RE, that is this. So, in the log plot it is a straight line. Okay. So, this is the regime in which we are operating, and you can see that here the friction factor appears to be independent of the surface roughness. As you go to the high Reynolds number regime, you can see that for different values of the relative roughness you are getting different values of the friction factor. So, the friction factor is depending on the roughness, but for fully developed laminar flow the roughness is apparently having no role to play, because all the perturbations induced to the flow because of roughness are attenuated. Perturbations do not amplify in a laminar flow. So, that makes it independent of the roughness, but still the analysis does not take into account the length scales of the roughness. So, the length scales of the roughness, they themselves can be important as compared to the system length scale when you are talking about microfluidic systems. So, it is worth investigating that what is the role of roughness for laminar flow through I mean micro channels of whatever geometry. That is the first remark that we have put. The second remark is that you see HF is proportional to mu QL by rho G pi d to the power dH to the power 4, hydraulic diameter to the power 4. In this case the hydraulic diameter is the diameter itself. So that means that the head loss for a given flow rate is inversely proportional to the fourth power of the diameter. So if you want to have a particular flow rate, then if you reduce the diameter from 1 meter to 1 micron, see 10 to the power 6 to the power 4, that is 10 to the power 24 times the head loss will increase. So you will require tremendous pumping power to drive the flow. So you cannot really achieve that high a flow rate in a pressure driven microfluidic system which you can achieve in a macroscopic system. You have to compromise with the Q, because to achieve the same Q you require to have a huge driving pumping power. Therefore you compromise on Q, but sometimes it is a blessing in disguise. Not in all applications you require a large Q. For example, you are administering a medicine or a drug to a patient in a very minute and precision quantity. So there you do not require a high flow rate. There in fact a precise delivery of the drug is what is important. So high flow rate may appear to be an important and useful thing, but it depends on the context where other factors may be more important than high flow rate. So these are the two important observations that we have made from our analysis so far. Now whatever we have discussed so far is something which we normally covered in the undergraduate first level course of fluid mechanics, but we want to go beyond that in this particular course. So now what we will see is that, like, we may still consider steady flow, but instead of a parallel plate channel it can be a channel where the width is not infinitely large as compared to the depth. So that means the width and depth are comparable. So how do you get a solution for such a problem? So we will try to address that. I would partially work out this problem and then leave the remaining part of the problem as a homework to you. So we will work it out partially. So we will first make a schematic to understand that what we are talking about. So let us say that you have a channel of cross section like this. Let us say this is y axis, this is z axis, and perpendicular to the plane of the board is the x axis, and the pressure gradient is applied along the x direction. So there is a dP dx. Let us say that this is A by 2, this is A by 2, this is B by 2, this is B by 2, and we are interested to find out the velocity, the wall shear stress, the dimensionless wall shear stress or the dimensionless pressure drop, the standard parameters with which we are interested. Now let us write the governing equation first before going for a solution, and to write the governing equation, I mean we can do a similar analysis like the parallel plate channel. still we are assuming that it is fully developed. Let us write the x momentum equation. Let us write the x momentum equation. Because it is fully developed, the left hand side is 0, steady and fully developed. The right hand side so let us write the viscous term. Now there will be